Last time we were looking at some of the results which get modified under the uh, availability of concepts like sets of measure 0. Good morning, welcome to Krishna's class. Now we consider this, take this problem further, and we have seen that some of the fundamental theorems that we have proved earlier valid for the entire x can be now relaxed, and we have given the idea how it works. Okay, so let us now look at more such results, and we shall prove the following. So we begin with the following. Let xm mu be a complete measure space. Now we prove the following results. The first one is suppose f is a non-negative extended real valued function which is measurable and let E be a measurable subset. If integral over E equal to 0, then f equal to 0 almost. Now recall that suppose you were to consider a non-negative continuous function on an interval 0 or on the interval. Okay. And has the property that integral over 0 1 of the continuous function is equal to 0. Then we can conclude that from this global property and the non-negative function, we can conclude that the function is 0. See, it goes like this. I'll just some example, actually. Take f belonging to 0 1 and assume f is greater than or equal. And m of course the Lebesgue measurable functions. So mu is the Lebesgue function. Then if integral over 0 1 f d mu 0. Then you see that you are actually doing the following: integral 0 to 1 f dx equal to 0 because f is continuous, and this implies f equal. You can, in the classical way, prove that if f is not equal to 0 at some point in 1, then because of the continuity, you can find a neighborhood in which the function is non-negative, and therefore you have a positive value for the integral otherwise. That's a classical proof, but this is true. Now, suppose we modify this. Okay? Now, this is clear. Suppose we drop the condition that f is positive, but not necessarily continuous. That means we modify the function at finite set of points. Okay? Let us say for instance, yes. Right? So, for instance, let us take the function f x to be 1 for x belonging to and this is equal to any value 2 for x belonging to 0 all over here, 2, 1, x belonging to 0, up, then f is not continuous. Now then you see that integral 0 to 1 fx dx is again 0. That means the function need not be identically 0 for the integral to be 0. That is, the function identically 0 for its integral to take 0 value. This is what we are familiar with. Okay, then what happens? But here you conclude that everywhere except at these finite set of points, the function is here. Okay? And what is this set? This set is a null set. It's a null set, and therefore, or in the parlance of the measure theory, it's a set of measures 0, of limit measure 0. Therefore, we think about a modification of this. Suppose the function is, we say, instead of just taking a finite value here, it can take a negative value, it can take a positive value, it can take an infinity, it can take a value infinity at this point, or it doesn't matter when it comes to integration, or measurability is not affected by it. Okay. So what we get here is a generalization, or what you can expect in general of this function. That means except possibly at a set of measures 0 in E, the function is 0 almost everywhere. Okay, let us prove this. It's actually almost everywhere, not on the whole of X, but on. Let us prove this result. So the moral of the story is, if the function is 0 everywhere, then obviously its integral is 0. But the function equal to 0, or the integral of the function equal to 0, does not necessarily mean the function is identically equal to 0, but all that you can assert is that it is 0 almost everywhere. That means except possibly on a set of measures 0, the function is 0. That is the conclusion that you can make. So let us see how we prove this. Let An be defined as the set of all x belonging to E, for which what is that you are doing? You are doing this. Takes values from here to here. Okay? And you are considering those sets. Suppose this is 1 by n. Then this part is what is called, okay. Then this is a set of all values greater than 1 by n. Okay. So all those elements in E which gets An gets mapped. That is F greater than for n equal to then what we have is the following. Suppose you take 1 by n is the value, is the minimum value the function takes on An. So 1 by n times the measure of An is less than or equal to integral over An of f du, which is less than or equal to integral over E of okay. So this is clear because An is measurable. An is measurable and An is a proper subset of for each. So what is the consequence of this? The consequence of this is that mu An This in turn implies mu an equal to 0. Mu an. Now, x belonging to V, for which union A. An is measurable, therefore union An is measurable. Okay. Therefore, the set on which An is greater than or equal, or fx is greater than or equal to 0 is now already taken care of. Okay. And the measure of this, since n, the set of all mu of which implies the measure of the subset of on which f is greater than 0 is of measure that is f is 0, f is equal to 0, almost every. That means f is equal to 0 everywhere except on a set of vectors. That is the meaning of this. And that's exactly what we wanted. Now this is on E, on any measurable subset of if non-negative. So then, now you see we are going to ask the following. Suppose you know that the integral of a measurable function with complex value for general case is 0 on all measurable subsets of E of x. Then can you conclude that f is equal to 0? We are not, see, we have said something. We said that we are no more assuming f is non-negative. But that side we have weakened the condition. But on the other side we have strengthened the condition. is that it is not just valid for some measurable subset, but it is valid for all measurable subsets. Then can you come to the conclusion that f is equal to all? Let's see. Now this is based on the proof essentially uses the result in theorem. Okay, so let us take, suppose L1 and equal to 0, almost for every b, every measurable subset, then so this is the objective of the theorem. The objective of the previous theorem was to support this theorem, the proof of this theorem. So here we are assuming two things. One, f is an L1 function. What is an L1 function? An L1 function is this, that is integral over x this is what you call f belongs to this is the definition. Okay, so that is one assumption. The second assumption is that f integral over e of f equal to 0. But this is the important for every what we have earlier proved is that if f is positive, non-negative, okay, f is non-negative on any measurable and integral f equal to 0 on that, then you can conclude that f is equal to 0 almost everywhere on that particular. Now we are going further to this. So this is the conclusion that we are making. Okay, let us prove this theorem. The proof of this theorem uses the previous result. Okay, so we are assuming f is complex. And we further assume this integral over x assumption. So let us put f is equal to u plus I. U and v are the real Yes. Okay. Both real values. Then we are real valued functions, but they form what is called the real and imaginary function. So let's we reduce the situation to something in the previous search. Let E be the set on which Ux is greater than Ux is the real part of this, and we take the collection of elements E where Ux is non-negative. Okay. Now E is measured. From the basic definition of measurability, it's true. And the real part of integral over E see, this is where the function, see, U is actually can be written as U plus minus U minus. Okay. That means U plus is the set on which the function is positive, otherwise it is 0, and U minus is the set on which the function takes again positive value but equal to 0, but then U becomes the difference of, as we have explained it, this is positive and negative parts of something. Suppose this is the function, and U, suppose this is, then U plus is, U minus is this reflection of over here. This part. So you have a U plus and a U minus. This is your U plus. Sorry. Yeah. This is your U plus. Plus U minus is something different. Color coded. This is U. So that the difference now becomes equal to U. That's easy. Now it is a set on which U plus. See, on E, this is integral over E, U plus. Integral over E equal to 0, and by the theorem 1, U plus is identical is equal to 0 almost everywhere on. Similarly, see, so you have a, actually the following. F is written out as follows. F is equal to plus minus 2 minus plus I to so you see that the integral of F is equal to integral U plus minus integral U minus plus I into integral E plus now we have worked with U plus, okay, and we have seen that the given condition assures that integral U plus equal. Now apply the theorem 1 to all these 4 real valued functions here not. So this is the conclusion, which in turn implies okay, because our condition, our assumption was integral over A from which we are concluding this. Now the next result. It's also something that we have done earlier and a generalization that. So the earlier we have proved that we called We call the theorem. Then this is a very standard result. Okay. And we make use of this result. So let us just briefly recall the proof. We put z equal to integral over x f. Then this belongs to a complex number. So there exists a complex number alpha with odd alpha equal to 1 such that alpha z is equal to 1. How do we observe this complexity? Take z. Mod z is the length. Mod z is a real number. Okay. Now what we do is we take alpha to be equal to z conjugate divided by okay. Then you see that alpha z is then alpha z that's the choice. So you take this is the complex conjugate of that z conjugate, and then what you are doing is this alpha you are taking as z conjugate divided by that mod of z conjugate. So you take the unit length complex number on this. That means on the unit circle intersection of this line is the corresponding z conjugate, or this is what you call. So if you multiply alpha with z, you will get the desired statement. Okay. So u equal to alpha. Then mod u is less than or equal to mod alpha f less than or equal to mod, because mod alpha is okay, therefore integral over x f nu which is equal to integral of alpha f which is equal to integral over x alpha f is equal to u. So u d nu which is less than or equal to okay. So what we have obtained, that's what we wanted. Okay. So we recall this theorem and we shall use this. So we shall state the theorem 3. Suppose and integral this is equal to then there exists a constant alpha such that now you see, suppose there exists a constant like this, then value exists. So what happens? Okay, this integral is essentially equal to integral of alpha f, because you can pull this alpha out and you will get mod alpha equal to 1 and integral over this. Okay, and that from that this will immediately follow. So one way it is true, that is if alpha f is equal to mod f, then this is true. So we have to prove the other way. For that, now note that the last inequality this is the one. Star. Okay. Last inequality star in the proof of the theorem we have quoted. Above is an equality. It's an equality under the given condition. Represent theorem. So this is the condition that we are. This is star just which implies integral mod f minus u is greater than or equal. Okay, which implies mod f equal to mu almost everything. Which in turn implies, now we will just apply the result of previous. You know, real part of phi f equal to f almost everything. Implies alpha f equal to mod alpha f is equal to. So this is the proof. So just use the previous one of the earlier results that we have used to prove this here. So I think I'll stop here. Thank you very much. So these are some of the properties that, and we will look at a couple of theorems about later. Thank you very much.